Oh boy, do I love when we get to this point of the course. It's like Christmas. Everything all comes together. Everything that we've learned about, we build on, and in this final learning unit, it sort of all culminates together. So this single learning unit is really a 30,000-foot flyover view of what the entirety of Biochem 2 is going to be about. And we start right now with sort of an overview of fuel metabolism. We're going to talk about the polymers that we learned about, the linkages that we have in those polymers that we need to break to make them into monomers so that we can get those out of our digestive tract. So we're going to learn this sort of slide here, talking about exogenous sources of fuel. So we're going to talk about things that you consume in your diet, need to get out of your GI tract, but just putting a little pin in the fact that, well, you have endogenous sources. We'll review that again once we get there. And then highlighting that this is really going to be very carbohydrate focused, very glucose focused for how we will learn metabolism. The same will be true next semester. And then we will map on and understand the similarities and differences for other fuels. So just big picture, just to start all the way up here at the top, we learned about 4 biological molecules, and 3 of them were polymers, right? We learned about proteins, which are polymers of amino acids hooked together by peptide bonds. We learned about carbohydrates, which are polymers of monosaccharides hooked together by glycosidic bonds. And the other polymer, true polymer that we learned about was nucleic acids built from nucleotides hooked together by phosphodiester bonds. Well, you'll notice that that polymer is not listed here, and that's because we really don't consider nucleic acids as a fuel. The other molecule that we absolutely consider as fuel are lipids, and that's not really a polymer, but we do consider a linkage. Okay, so importantly, we're going to review the polymers that we learned about, the monomers that we obtain when we have hydrolysis of linkages. So we're going to talk about hydrolysis of linkages. Okay, let's actually put linkages over here. So hydrolysis of linkages. So some pieces to review here, specifically when we're talking about proteins, carbohydrates, polysaccharides, and lipids, right? I want us to remember some important things. So let's start over on the lipid side, because that's the simplest in terms of the atoms that are contained. So when we refer to them just as hydrocarbons, and that's because they contain carbon and hydrogen. Polysaccharides, carbon, hydrogen, and we introduce oxygen. And then proteins, carbon, hydrogen, oxygen, and then importantly, there's nitrogen. Every amino acid, remember, has nitrogen. And then we've got 2 amino acids, methionine and cysteine, that contain sulfur. And I'm going to put a big circle around nitrogen because we're going to address that in just a minute. So here's the atoms that we create these polymers from. So again, thinking about the atoms that we create these from, and importantly, I want us to be able to think about their caloric value. How many calories per gram? Well, proteins and carbohydrates are both worth the same, 4 calories per gram. Lipids are worth 9 calories per gram. We'll get into the weeds next year as to why, or next semester as to why, but remember what fuel metabolism is. We take fuel, combine it with oxygen, give us carbon dioxide, water, and energy. So the degree that that fuel is already oxidized is going to be directly correlated with how much energy it's worth, in the sense that if we've already metabolized or oxidized our fuel, for example, if we have carbohydrates here that already have oxygen, they are not worth as much. We're going to talk about sort of a sponge analogy here. If we've got a fuel that is our sponge and the electrons that hold that fuel together are water, and the more reduced a fuel is, the more electrons and water it has. So when we talk about squeezing the energy out of our fuel, we're really squeezing the water out of our sponge, and we need to collect that water, those electrons. Well, with that analogy, we would say that a carbohydrate sponge does not have as much water as a lipid sponge. We can squeeze more electrons, more energy out of a lipid sponge, right? Oxidation is the loss of electrons, so it's the loss of that water in our sponge analogy. And so we're going to be able to harvest more energy from lipids. Lipids are worth 9 calories per gram. Specifically, when we are going to be studying these from sort of a metabolism standpoint, we'll be talking about triglycerides. Okay, one last little piece here to put on is that when we are talking about where these fuels come from, we are really talking here about dietary sources. So dietary sources, so we're going to refer to these as exogenous. Okay, and so we are going to be consuming these and then we're going to get them into our GI tract, and we need to get them out of our GI tract and into the bloodstream. So we're going to talk about these fuel molecules in our GI tract, and we need to get them out into the bloodstream. Okay, so highlighting, and just we'll see this in another point in this diagram in just a minute here, but highlighting when we talk about exogenous meaning external sources of fuels, these are proteins, carbohydrates, and lipids that are the macros that we consume in our diet. Now, when we think about endogenous sources of these, there are intentional sort of endogenous stores of lipids, right? That's our adipose tissue. There are intentional reserves or stores of carbohydrates, that's glycogen, that's in liver and skeletal muscle. Now, there are unintentional reserves of proteins. You don't have proteins in your body that the intent is to break those down and be able to use those for fuel, but you do have them. Specifically, your liver and your kidney will be things that atrophy first if you need kind of amino acid building blocks. But sort of from a kind of a macro standpoint here, we need to consume, right? All of these are an important component of our diet. But I want to highlight that when we really think about consuming things for fuel, it's carbs and it's lipids. That's what we consume from a caloric value. When we think about proteins, I don't want you to think about consuming proteins for energy or as a fuel source. The purpose of protein consumption is largely as a building block. We take those amino acids and we either rebuild them into new proteins, or we take those amino acids and we convert them into amino acid derivatives that we need. All stuff that we will get to next semester. Okay, so building on this important sort of slide here, 30,000 foot view that we're going to be zooming sort of in and out of. Okay, let's review again the linkages that we have. So amino acids are linked together to make proteins, and they're held together by peptide or amide bonds, right? That's our linkages. I'm going to be doing that a lot when we talk about hydrolyzing those linkages. Reviewing again, when we just had our enzyme catalysis chapter, that is going to be those serine proteases that do that digestion in our digestive tract. When we talk about monosaccharides that are hooked together to make polysaccharides, we've got glycosidic bonds. And I'm going to highlight that we are going to be very glucose focused as we consider sort of fuel metabolism here. And then lastly, when we think about lipids, we do have a linkage. It's not a polymer linkage, but it's a linkage that we have with triglycerides. It's going to be an ester linkage that hooks that carboxylic acid group of fatty acids onto the alcohol group of glycerol. And that's how we're going to link those together to make our triglycerides. Okay. Hopefully all review so far, right? What we're going to now talk about, and we've already watched that other video, that short video that sort of talked about that 30,000 foot view of 4 important metabolic steps, okay? We've got glycolysis, we've got pyruvate dehydrogenase chemistry, we've got the citric acid cycle, and then we've got electron transport and oxidative phosphorylation. We're going to see how those all come into play here. We're going to label them with numbers 1 through 4. We're going to have individual slides to study sort of the 30,000 foot view of each of those steps. But just as a preview, next semester, each one of those becomes its own learning unit. But what we're going to learn right now in terms of the single slide piece, that's going to be your fundamentals quizzes for next semester's course. Okay. So remembering that we're glucose focused, let's sort of highlight what's happening here, right? We are going to have the outside of the cell, that is our bloodstream. We've got glucose floating around in our bloodstream. We need to get it inside of the cell. We've already talked about that. We've already talked about how we get glucose inside of the cell. We've got GLUT transporters, right? GLUT transporters can get and transport glucose out or glucose in, right? We're not going to highlight here, but just remembering that we've got GLUT2 transporters that are on liver that are always present. We've got GLUT4 transporters that are present on skeletal muscle and adipose tissue that are insulin sensitive. They respond and are circulated to that surface when we've got elevated blood sugar, elevated insulin. Okay. Remember I said I was going to make a distinction between exogenous and endogenous. Once you get inside of the cell, the biochemistry does not really differentiate whether you had an exogenous or an endogenous source of that fuel. So once you are inside the cell, exogenous is pretty much the same as endogenous. We don't need to worry about sort of what the source is, okay? So once we're inside of the cell, we say we are cytosolic. Cytosolic. Okay. One of the things that will be a hallmark of things we'll study and learn about with these different metabolic pathways is where they occur. And in general, we're going to be talking about processes that occur in the cytosol or occur in the mitochondria. So we have each one of these sort of like little sort of tan lines here represents, let's actually write this on here, these represent lipid bilayers, right? Lipid bilayer, right? So when we talk about in our membrane transport chapter, we learned about when you have a lipid bilayer, you have to have some type of a transport mechanism for things that are hydrophilic. All of the stuff we're talking about here is hydrophilic. So getting across the lipid bilayer of the mitochondrion is also going to require transporters, moving metabolites in and out. So again, once we're inside the mitochondria, we will say that we are mitochondrial. Now, an important piece to highlight here, when we distinguish where and when processes will occur in the cytosol or the mitochondria, very often an easy delineation will be whether or not you are in an aerobic or anaerobic condition. If you want to dip in and do biochemistry in the mitochondria, it's generally going to be under aerobic conditions that require oxygen. So we are going to be aerobic and requiring oxygen. Now, we're always going to have sort of exceptions to rules, but in general, we're going to learn things as sort of this umbrella of generally always the case. And when you do biochemistry in the mitochondria, it tends to be when you are under aerobic conditions. Okay, so coming back here, we're going to again highlight these 4 steps. The first one that we have here is glycolysis. Glycolysis converts glucose to pyruvate. So I'm going to highlight here. See, I'm going to choose purple for here. I'm going to highlight different points where we have substances that we call branch point metabolites. And you can see on the slide here, they might be referred to as sort of common metabolites, but we call them branch point metabolites. And branch point metabolites have lots of arrows that lead into or out of them, right? They sort of represent central hubs of metabolism. And pyruvate is a very key 3-carbon metabolite, as we'll see down here. Acetyl-CoA is a very important 2-carbon metabolite. So again, just highlighting with one single arrow here, we show glycolysis. We're going to expand on another slide in this learning unit to learn about sort of the fundamentals of glycolysis. It will be one slide. That will be what you need to know for your final exam for Biochem 1. That will be your fundamentals information for Biochem 2 for that quiz. But then we'll have an entire learning unit on all of the ins and outs of glycolysis. Okay, but the purpose of glycolysis is we break glucose apart into pyruvate. It doesn't show it here, but we actually make some NADH in addition to that ATP, okay? But you'll notice that this is occurring in the cytosol. Now we're going to take that 3-carbon pyruvate and make it into a 2-carbon acetyl-CoA. Acetyl-CoA, another one of those important branch point metabolites here, okay? And here is where we start seeing some carbon atoms get liberated as carbon dioxide. Oh, and hopefully remember, we don't have carbon dioxide bubbles floating around in our bloodstream, right? We've got carbonic anhydrase that converts it into bicarbonate. But we're going to start to see, let me write this down someplace important here. Remember, this is our main equation. Fuel plus oxygen gives us carbon dioxide, water, and energy. And when we highlight the forms that that energy can come in, we've always said that that's ATP, but as we'll see here, you can have NADH and FADH2 that can be used to make ATP. So what I wanted to highlight here is we are starting to see some places where we generate and liberate that carbon dioxide. So let's do that here. Let's highlight places that we're going to see carbon dioxide get eliminated. Okay, so coming back here, let's highlight, this was the second step that we saw in our video. That was sort of that overview. Not labeled here, but this is pyruvate dehydrogenase chemistry. So this is pyruvate dehydrogenase, PDH. Okay, I'm going to encourage you to keep up your Alphabet Soup Excel workbook. You can keep using that same one that you use for Biochem 1, start a new one for Biochem 2. There are a lot of acronyms that are still to come here. PDH is pyruvate dehydrogenase. Okay, so now we are at acetyl-CoA. Okay, you'll notice that starting with this second step here, second stage of glucose metabolism, we're in the mitochondrion. Okay, now we're going to go into the citric acid cycle. Citric acid cycle was sort of the third step. Citric acid cycle takes acetyl-CoA and ultimately converts all of these carbon atoms to CO2. So again, here is some additional CO2 that we're liberating. But importantly, remember we've got this sponge analogy. We're squeezing energy out. We really haven't done a lot of energy squeezing out in glycolysis. We do a little bit. We generate a little bit of ATP, a little bit of NADH, but it really is the citric acid cycle. That is the workhorse of generating energy molecules, ATP directly, and then mostly we're harvesting that water from that sponge, those electrons from those molecules as reduce cofactors, FADH2 and NADH. Remembering your B vitamins, vitamin B2 and vitamin B3 are necessary for these guys. Okay, so we've got now the citric acid cycle that has liberated all of our carbon atoms as CO2, and now we've got all of the energy stored as these molecules. Now, one thing that this slide doesn't have that I'm going to add on is these FADH2 and NADH molecules go to the electron transport chain. And I cannot spell electron transport. And so the electron transport chain with oxidative phosphorylation, right? ETOP. This is that fourth step. Remember what the purpose of that is. The purpose of this is we are going to use a proton gradient that's generated by moving electrons through an electron transport chain, and we are going to be able to use that to make ATP. Now, they don't specifically show it here, but let's map on here that the final electron acceptor, okay, from the electron transport chain is we are going to deliver these electrons. They're going to deliver them to oxygen, and that oxygen then is reduced to water. Oh, lo and behold, here is the other product, waste product that we have, right? Carbon dioxide and water, okay? And we've highlighted, here's all of our energy pieces, right? We've got ATP, we've got FADH2, which ultimately gets used to make ATP, right? But there's all of our energy pieces, okay? Let's find little turquoisey there, right? There's our oxygen. So we can see where all of these pieces are sort of mapping together. Okay, one last little piece that I need to highlight here, and it's why I put this in hot pink here. We have an elemental problem, pun intended there, when we have proteins that contain the atom or the element nitrogen. Eliminating nitrogen is not super easy. The carbon atoms, the hydrogen atoms, the oxygen atoms, those sort of all get eliminated through the waste products of carbon dioxide and water. What we need to think about is how we eliminate nitrogen, and we are going to eliminate nitrogen through the urea cycle. Okay, so urea is essentially how we are going to be eliminated. Now, we do it as urea. Other organisms will make ammonia, and that's sort of how they eliminate their nitrogen. But that is a big piece of what we will study next semester when we sort of look at protein metabolism. But wow, involved sort of slide here. This is going to be one I encourage you to sort of refer back to time and time and time again as we sort of dive into the weeds here. Be able to sort of step back out and sort of look at this 30,000 foot view. So again, learning it to start, very carbohydrate focused, but I just want to come back here and highlight really quickly. When we take triglycerides and we break them apart into our glycerol backbone, 3 carbon atoms on my glycerol backbone, that gets converted into pyruvate. But you'll note here that fatty acids get broken down into acetyl-CoA. And this is a super, super important piece here because this arrow is one way. We've talked about the word gluconeogenesis. Gluconeogenesis is how you take pyruvate and you can make it back into glucose. And this is super, super key. I will say it tons and tons of time. Fatty acids can only be broken down into the 2-carbon acetyl-CoA piece. This cannot go back and make pyruvate, so it cannot be used to make glucose. So fats cannot be used to make glucose. Okay, that is a super, super important piece there. But that's again how we can get energy from fatty acids. Highlighting amino acids. When we talk about amino acids, when we drew amino acids last semester, right, we had an amino group, a carboxylic acid group, and then we had an alpha carbon that had those different side chains. When we talk about metabolizing amino acids, one of the first things that we do is we get rid of the amino group and we're left with what we call an alpha keto acid skeleton. That is either going to resemble the branch point metabolite pyruvate or the branch point metabolite acetyl-CoA. Those can, though, go on and just be metabolized like so many other things that we have get metabolized. But importantly, we're going to learn about how that nitrogen piece is ultimately eliminated as urea. But great 30,000 foot overview slide that introduces us to metabolism.